don't need to start recording yet, right?
That's fine. They'll edit it anyway. Okay, so this morning we're going to have Wynn Ho from the University of Southampton tell us about how one can test nuclear properties from observations of neutron stars.
Thanks. Pleasure to be here. The first thing is, let me acknowledge my collaborators. It's a long list, but I'm actually going to, and though it's not like we all worked on the same project, I'm going to talk about 4 topics, and so each one contributed to to one or more of the topics and stuff. The other disclaimer I'm going to make is that I'm not going to talk about, like I said, I'm going to talk about 4 topics, and given the interests of the group, I'm not going to get into the astrophysical nitty-gritty details. Okay, I'm happy to answer questions and discuss them, but I don't want to get too bogged down in the details of it and stuff. Okay. And it's unfortunate that Nils isn't here, so I can pay him a compliment and the other organizers, because I think it's my talk is well placed in the week. In 2 ways. One is that on Monday and Tuesday, Andrew and Simon and Cole talked about determining the mass and radius and getting the nuclear equation of state. And then we kind of, in Tuesday's discussion, we kind of were saying, well, what if we were able to measure the mass and radius definitively? Should we just all go home and that's it? Right? But from yesterday's talks, especially Omar's, we learned that it's not just about the mass and radius and the equation of state. There's more to it. There's transport properties, and so I'm going to talk about that and also superfluidity and superconducting properties. So other things besides just nuclear equation of state. Okay. The other theme of my talk is that, again, Andrew, Simon, and Cole started off with the big, the neutron star. Right? And then yesterday we moved to the small, the nucleus. Right? And now we're going to move back out to talk about the big neutron stars. And so that'll be a theme that I hope comes out in my talk today. So, I should say, so obviously this is the Cassiopeia A supernova remnant. I like showing it because it's such a beautiful picture. What you're seeing is, the explosion material from the supernova, and it's a multi-wavelength image. The red is infrared from the Spitzer telescope. Yellow is optical from Hubble, and the blue and green is X-rays from Chandra. And what's nice is that the remnant is about 10 light years across, okay, but you can actually see the neutron star, and that's this blue dot here. It's bright in X-rays. You can't see it in optical or infrared. Okay. And so in the context of the remnant, the neutron star is small, but obviously it's big compared to the nucleus. And so again, this is just a zoom in of the remnant and the neutron star, artist's impression, obviously. And to put into context, we're talking about a neutron star that's about 25 kilometers across, right? And so for those of you who made the journey on Saturday to LIGO, it's about 300 kilometers, and so you traveled across about 12 neutron stars in that distance. Okay, so it's yeah.
And almost as hot.
Another way to put it is that you can fit a neutron star well within the Earth's atmosphere. Okay. So the 4 topics I'm going to talk about where we can use neutron stars to test nuclear properties is looking at the equation of state from looking at QMXPs. Again, we talked about this on Monday, but I'll reiterate it and describe briefly what QMLXPs are. and why we look at them. Then I'll talk about the equation of state and superfluidity and superconductivity from the Cas-A neutron star. And then equation of state and superfluidity from looking at the pulsar glitches. This, Andrew mentioned this. And then talk about gravitational waves from R modes. And Simon talked about this, but I'll have a different, more to say about it. Let's see. So, which?
There's the one right in the middle with a red dot on it.
Oh, okay, great. Okay, so let me just briefly say how we get mass and radius from X-ray spectra. And so to get the equation of states. Okay, so this is a plot of this X-ray spectrum, two X-ray spectra from the Cassiopeia A. So it's just flux or counts as a function of energy. Okay, and you fit, so you get this, observation from a telescope, and you fit the spectrum with a model. Okay, and the most simplest model is a black body, and that model fit will depend on basically two parameters, or three if it's a ratio. Is that depends, if it's a black body, it depends on the temperature and the radius over or distance, right? It's a black body, so obviously black body only has one parameter, it's temperature, right? But if you think about, you put a hot object out into space, right? It's going to emit as roughly as a black body, so it depends on the temperature. And also how bright it is, right, will depend on how big is it, the radius, and its distance. Right? The further away it is, the dimmer it is. Right? So it's obvious that fitting the spectrum, it should depend on these parameters. Okay? You can go with more advanced models and consider an atmosphere, or like the sun. The sun does not emit as a black body because you're looking at the photosphere of the sun, and so you have to account for the opacities, what the abundances of different elements in the atmosphere of the sun. Same thing with a neutron star, and so those things will give you things like the redshift, which depend on m/r, or surface gravity, depend on the composition of the atmosphere, and things like the magnetic field. Okay. And when you do that, you do that fit, and you get some mass and radius, and you put it on the mass radius plot, and hopefully, you can then learn something about the equation of state, right? Because the equation of state tells you the mass and radius of the neutron star. Right? So the first topic we're going to talk about is the neutron star radii from QMXBs, quiescent low mass X-ray binaries in globular clusters. Okay, so why are these? Why do we look at these sources? Why are they important, right? or useful? Well, first, a QMXB is a binary system, where you have two stars. One of them is a neutron star, and the neutron star is accreting matter from a low mass companion. Okay, so because of it's accreting, it's X-ray bright, so that's why it's useful. Okay, because it's X-ray bright. Also, so the ones in globular clusters are useful is because they are have a relatively well-determined distance to roughly 10 to 20%. Okay, one of the most difficult problems in astronomy is knowing distances to objects. So if you know the distance to 10-20%, that's pretty good in astronomical terms. So again, the spectral fit depends on the radius over distance, so it's important to have. So these are the reasons why these sources are important. And so, as we discussed, recent results by Sebastian Guillot used 5 of these QMXBs in globular clusters and constrained the radius to 9 plus or minus 1.5 roughly, and that's shown that by their plot here, mass and radius. Okay, and so obviously this is on the low end, as has been mentioned before. But one of the things to keep in mind is that if you look at the 5 sources, okay, you have 6397 has a very small radius. Omega Sen has a very large radius, whereas the other three are very typical, okay, 10 plus minus 3. And so in their analysis, they actually do this. They say, let's exclude the very small one. Well, what do we get? Right. They get 10 plus, if you exclude the very small one, it's strong. So this is very strongly biased by the smallest one. Right. And so if you exclude it, it roughly falls in line with what Andrew and Jim got. Right. And this is their plot of the constraint on mass and radius.
Sorry, so this 9.1 number under the assumption that they all have the same radius?
Yes. Yes. So I'll show how you build it up, but basically it's under the assumption that they all have the same radius because it doesn't matter what their mass is, as long as they're roughly between 1 and 2, they should have the same radius.
Is there anything special about NGC 6397 in X-ray, or is it very typical?
It's fairly typical of these. The 5. Well, I'm only really familiar with 4 of them. There's only one of them has very little data and stuff. We haven't worked on that one. But.
When I'm not understanding something, maybe you
Sure.
can help me. The radius 9.1,
Yes.
the one in red, but you say NGC has 6.6.
So this is the under the assumption of that they all 5 have the same radii. This is what they get by combining the radius determinations of all of them.
But if they relax that assumption?
If they relax that assumption, for example, kicking out the smallest one, 6397, this is what they get. So only four neutron stars instead of the 5.
Yeah, but how did the number 20 kilometers come from Omega Sen 1?
So this is, again, fitting the X-ray spectrum.
Oh,
So they fit all 5 systems independently, okay, and get these values, and then they say, well, can we, because it's a contour plot within this plane, they say, well, what can we get them all to have the same radii? Is there some probability distribution that says that they all have the same radii? And they can, and that radius turns out to be this.
Well, this confuses me more. According, what is your take on what should be the right way to go?
Okay, so let me show this. So this is, so we looked at 2 of the sources, basically the smallest one and the largest one. We've already done work on, like I said, 2 of the 3 here. Okay. So this is what you get for the mass and radius, the kind of the confidence contour region. When you fit the X-ray spectrum, this is what you get. Okay, this is for Omega Sen, and this is for 6397. Okay, when you assume a hydrogen atmosphere, a model spectrum to fit to the data. Okay, so as they found, we get a small radius for 6397 and a large radius for Omega Sen. Okay, but we do get a much smaller radius than for Omega Sen than what they get. Okay, this is due to different, again, astrophysical details, distances, absorption, and so forth. I won't.
Can you not get an independent measurement of the mass, like from X-ray?
No,
That's
not for these ones.
You could imagine getting a
Well,
better constraint if you had a lot more data.
yes, sure. I mean, but we don't have one at this time. Okay, so the idea is let's just take these 2 systems and see, can we construct a mass radius line, right, that goes through both of these? And the answer is basically no, right? Because 6397 has to have a radius within here, right? Omega Sen has to have a radius within here, right? So the only place I can put it is kind of here, right? So it's a very small radius, right? Basically, not the same number, but the idea is the same, right? I'm trying to get where a single line, vertical line that goes through both of these regions. Right?
So the part that I'm missing now is why do you want to insist that there is a single radius?
Again, because if you look at the equation of states, most of them are basically vertical for the reasonable values for the
So you're
mass.
making the assumption
Yes.
that their masses are in
Yeah.
an
Roughly one. Well, I mean, you can see that over the range of 1 to 2, which is the typical values, right? It's a reasonable assumption. I mean, it's not in detail correct, but it's reasonable.
Is the quadratic equation of state 3 is not taken care in this case? That has a very defined equation.
Yeah, so it has obviously it's not vertical and stuff, but again, I assume that Sebastian Gil and them, they're basically considering nucleonic type equations of state.
Same radius or within an error bar? Sorry.
Hmm?
Just have to ask that.
What's that?
Is it same radius within a certain error bar?
Yeah, so I mean the errors.
that's
Yeah,
the one.
that's okay. So their value is given by these dotted lines here. Okay, that's 9.1 plus or minus. Okay. Yes.
If I might just, to me, it seems like depending upon how you do the statistics, how you choose your sample and who does it,
Mm-hmm.
the numbers seem to be changing. Am I getting that impression?
Yes. I mean, again, it's a part of. I mean, I guess your question is because we're getting very different values
Yes.
for mainly for this one, but it's because again we also, like I said, there's astrophysical details that in terms of distance, abundances, but also we have more data on this one that they did not have.
So Megasen has a huge error bar. What is it the core distance or what is the?
Well, it's not huge. Relatively, it's about 30%. Right? It's the same as these are about 30%. Yeah. And when we get this, it's about 20, 30%. It's not. I mean, we don't improve the relative error that much, but yeah.
I have a follow-up question. Could any one of these systems be revisited with more data taken
Yes.
so that the error bars could be reduced?
The error bars from the spectrum, no, because it's kind of a systematic, like I said, it's the distance, if we knew the distance better, right, and we're not getting the distance itself from the X-ray spectrum, right? So other observations, and that's what I'm mentioning, is for 6397, instead of just looking at the X-ray spectrum, we had Hubble observations. And what we looked for was hydrogen in the companion. We're looking at the companion star, because if it has one of the issues that was mentioned by Andrew and Cole is that this is assuming that they have hydrogen atmospheres, right? And these are accreting systems, right? Accreting from the companion. So if they're accreting hydrogen from the companion, then they will have hydrogen atmospheres. Right? But if the companion has no hydrogen, right, then it will not be accreting hydrogen, and it will accrete, for example, helium. And what we found was that the Hubble observations places a constraint. We don't see any hydrogen on the companion. Okay. It's not saying that there isn't, because we get an upper limit. Okay.
What is the upper limit?
I have to check. I don't remember the number. Sorry.
It's way below constant, right?
Yes. Yes. Well, I mean, it's below the for the type of star that it is. Well, the temperature and luminosity class of the star.
Yeah.
It's yeah.
So Hubble can't get helium abundance on that?
So we can't get. We were looking for hydrogen signature, the H alpha line, and we didn't see any. And so it's possible that again, this is a terminology issue, but astro terminology. It's possible that the system is ultra compact low mass X-ray binary, and the companion is a white dwarf. Actually, it's possible. We're not saying that it is, but it's possible it's a helium white dwarf. In which case, the neutron star would be accreting helium.
So in terms of future observations, I'm inferring that you don't see any lines, right?
Yes.
But if you were to be able to have a really deep
Well-
observation of sea lines, could you get radial velocities and periods to
Yes.
confirm the ultra
Yes.
compact?
Yes. Yeah. I mean, if you're on the TAC, by all means, accept our proposal.
I can either confirm those or not.
So if you make that assumption instead that the neutron star in 6397 is accreting helium, and therefore has a helium atmosphere, and you use a helium atmosphere model to fit the spectrum instead of a hydrogen, this is the region that you get for the radius. Okay.
But in all of this, a mass independence has been assumed.
Yes, yes.
For,
Well, no. Oh, well, for the fitting X-ray fitting spectrum, no mass has been assumed. But then let me, if I again make the assumption, mass independence, that can I fit 6397 in the same with a vertical line through omega sen? Obviously, I can, and if well fits within Andrew's and Jim's radius constraints, which is these dashed lines here.
So when you've made a case that Cas A is a carbon atmosphere, if you were to make these carbon atmospheres, how far would it shift to the right further?
For carbon, let's see, I don't think we've done the fit for carbon, but there are other reasons why you might not. I mean, you could again, you could try to fit it with carbon, but there are reasons for not, and I can come to that in Cas A if needed and stuff. So, but yeah. Okay, so the point here we're making is that it's possible that one of the 5 of these QMXPs has a helium atmosphere. Okay, and therefore, if you say that 6397 it does, then you can get a radius constraint well within the line that Andrew and Jim have. Okay. Other comments?
Is there any other? Say you ended up seeing some hydrogen or evidence of hydrogen. What would be your explanation for the low radius for 6397? Is it the hotspot? Is that?
I mean, yeah, you could make an argument that it's not the whole neutron star that's emitting.
So maybe pushing Cole's question a bit further. If I really wanted to ask, given the observations and freedom in my models, for instance, assuming what the atmosphere is made of and so on, how high could I push the radius? So let's say NGC 6397 is the one with the lowest radius measurement, right? Could I get it to be 15 kilometers? Could I get it to be 20 kilometers? Is there a limit to how you could push it?
Okay, from the X-ray spectra itself, you wouldn't be able to, if you put it with carbon, from experience, I would say that you couldn't put it up to, 18. You could probably put it up to 14 maybe, 15, but the reason why you wouldn't expect carbon is because hydrogen or helium would naturally float to the top, and these neutron stars are, well, I mean, I'll come back to it when I talked about Cas A. I think.
Yeah, and for partial surface emission, if you get it, which is semi-centered on the rotational axis, you can get it 20, no problem.
If you centered on.
So in other words, you don't see pulsations.
Right.
So it can't be well offset. A partial surface emission can't be well offset. But if you have partial surface emission, there's enough centered on the rotational axis, you see no pulsations, you could make this a 20-kilometer star, right?
Yes. Yeah, I guess. Yeah. So let me move on to talking about Cas A. And you can obviously, we have, like I showed, we have X-ray spectra, and again, you can get the mass radius from just fitting the spectra. these are the things that you get out of fitting the spectra and the ways you can get mass radius and stuff. There's obviously redshift, there's brightness, and surface gravity. Okay, that weighs into the model and the extraction from the X-rays, fitting the X-ray spectrum. And so when you do that, you just fit the X-ray spectrum of Cas-A. This is the mass radius constraint that you get. Okay, so it's our 68, 90, and 99% confidence contours. Okay, so Cas-A is not very useful if you just fit the X-ray spectrum to try to get mass radius from. Okay.
So can you explain the contour in the color?
Okay, so
The contours.
yeah, the contours are just the X-rays, the fit to the X-ray spectrum. Okay, this region here, this band, okay, is encompassing typical equations of state, what they predict for the mass and radius. So most or many equations of states fit within this region. Okay, so it kind of goes to Amitapa's issue of plotting individual equations of state. Rather, let's plot a band. Okay, and this is and then overplotted, you see three
I meant the
equations of state.
greenish.
Yeah, so this band is where
that's the
many equations of state fall. Okay. So yeah, we were, I guess on Tuesday's discussion, we were discussing what is the width of that. So yeah. So, like I said, by itself, the X-ray spectrum doesn't tell you a lot about mass radius and the equation of state. Okay, but one of the important points I want to make here is that you can get a lot more out of the Cas-A because you observe cooling. Okay, and the cooling can tell you a lot more than just mass and radius, because it depends on detailed equation of state information. For the cooling, right, to know how an object cools, like the neutron star, you need to know particle abundances. Right? You need to know the neutron fraction, the proton fraction, the muon fraction, because those contribute to the cooling processes, and they also have heat capacities. Right? So cooling model requires that information. So if you measure it and compare it to cooling model, you can get more out than just the equation of state. Well, I mean, just the mass and radius, I should say. And also, obviously, also, the cooling can depend on if the matter is superfluid or superconducting. So again, you can get more out of it. And so that's what I'm currently working on. I'll hopefully finish writing up the paper this week. Is looking at using constraints from the spectrum and the cooling, trying to fit the cooling data with in order for me to calculate a cooling curve to match the observations, I need to take an actual equation of state. Right? I can't just assume some mass and radius and get at the cooling. I need an actual model. Right? So the three available to me are APR, BSK20, and BSK21. Okay. And it's the three themes. This is the third theme, is that I'm using these because I have them available to me as an astrophysicist. Okay. Because they've been APR was given to me by Danny, but the BSK20, BSK21, I have useful parameterizations of the equation of state. Not just pressure as a function of density, but also the particle numbers as a function of density. And if the effective mass as a function of density, for example. And so it's important work by Sasha and Nico and stuff for providing something like this. Okay. Yeah.
So to incorporate the cooling constraint, I presume you need to know the age of the object.
Yes.
The initial temperature. How well do you know?
We don't know the temperature, but the if you know the age, cooling curves are generally we're fitting to the temperature evolution. So if you know the age, then the initial temperature is kind of given to you. Okay. But the age is fairly well determined. It's 320. It's the Wynn and Wynn off is about 1681 plus or minus 19. Because the way to do that is that because Cassia is so well observed, they can observe the motion, the expansion of the remnant, and so they can measure the velocity, and so they can backtrack that and get the age that way. So I'm not going to talk about some of the. So I'm going to make the assumption that the cooling is, just by normal modified Urca or Cooper pairing. I'm not going to consider other exotic phenomenon, and these are some of the works that have considered that. And we can talk about this in the afternoon discussion or afterwards or something. But Armin's got one here too. Yeah.
Is that inferable that which type of Cooper pair is neutron Cooper pair or more like kaon?
It'll be. This is all nucleonic matter, so it's neutron-neutron. Yeah. So if you do, okay. So first, I'm going to take these three equations of states, and this equation of state predicts a mass and radius. Right? And so I'm going to take that mass and radius and see if that mass and radius, how does if I use that in the atmosphere model, how does that fit the spectrum? So right now I've not done any cooling fitting. Okay, I'm just saying for that equation of state, it predicts a mass and radius. Do those mass and radii fit the spectra? Right. And so what these lines are the three equations of states. Okay, and the numbers are the reduced chi-squares of the fit to the X-ray spectra. Okay. And so you can see that the best fits are I've highlighted here in red.
What was the fit then again? I missed that.
Okay, so let's take APR. Okay, so at 1.4 it predicts a radius of about 11.6 roughly. Okay, so I take 1.4 solar masses, 11.6 and I use that as the input for my atmosphere model because the atmosphere model depends on mass and radius. Right? So I use that and I see, well, that spectrum, how does that fit to that model spectrum fit to the data? Okay, and it gives a reduced chi-squared of 1 here. Okay, and so and I do that for each. And so you can see that overall it fits in line with the previous plot, the contour.
You need to assume something about the composition.
No, at this point, no. I'm just using, again, the X-ray spectrum I only can get out mass and radius. Right? So you can see that, the best fit, it fits that contour, which was roughly here. Right? It's not surprising. Right? Another way to look at it is, this is the mass chi-squared. So these are roughly 90%, 1 sigma. So we're constraining the mass to within this range. Same thing here with the radius. Okay.
When Danny and I, Jim and Andrew, we looked at the variation of masses for the cooling curves. We didn't see a whole lot.
Yeah.
Is that what you're also finding?
Well, I'll get to the cooling in a second. Okay, so now we're going to, so that was just fitting to the X-ray spectrum with particular equations of states. Okay, so now let's look at what those equations of state predict for cooling and how do they fit the data. Okay, so to do that, one of the things I want to test is superfluidity and superconductivity, and I need the gap energies. Okay, so I've compiled superfluidity, superconductivity depends on gap energy, which you can translate into a temperature. So when the temperature in the neutron star, in that location in the neutron star, is below the critical critical temperature, the matter becomes superconducting or superfluid. Okay? And there are three types of superfluidity, superconductivity pairing in the neutron star that are important. One is in the inner crusted core, there's a neutron singlet. Okay? In the core, there's proton singlet, and in the core, there can be neutron triplet. And so that's what. And so I've parameterized different models for what this gap energy is. Okay? So these are the 9 neutron singlet that I've looked at, 9 proton singlet. So this is in the crust, this is in the core, and this is the neutron triplet in the core, the 8 that I've looked at. Okay. So, and I should say I've parameterized it. Okay. Because I don't have astrophysically useful information from the people who calculate. So these are actually kind of my rough by eye fits to. Usually, if you look in the literature on the gaps, they have a point here, a point there, and then maybe a point there. And so I'm just trying to fit to it with this parameterization, okay? Because it's the best I can do. Okay. If nuclear physicists can give me something better, some better parameters, I'm happy to take it. Okay. Yeah, and the other caveat is obviously if in the ideal world where I knew the nuclear equation of state, I should be able to calculate the gap consistently, right? But I'm treating those as independent because I don't have that information. I don't know it.
For your purpose, it's plenty good.
Yeah.
From our experience.
I wouldn't take those gaps from 70s where we didn't know really how the potentials are. So there is really, one should make a more, educated selection of the gaps because those from the early days are not based on realistic potential.
I mean, I'm happy to take advice input as to what to use, but yeah. And I also want to acknowledge Stefano for his helped a lot in terms of getting 3 of these curves the way he's plotted it and stuff. So yeah.
So you don't have any triplet gaps that peak at 6 times 10 to the 8 Kelvin, which is 3, or they're all higher?
No, they have some that some of them do. So if you do that, okay, this plot is old. Some of you probably saw this in Florence several months ago. I've actually done a lot more work on this, so don't take these numbers seriously. Okay, it's just an indication of what the idea behind what I'm trying to do is. So for each equation of state, mass and radius, I combine it with one of the gaps for 3 gaps. One for each type of superfluidity, superconductivity, right? And I calculate the cooling curve. I say, does that cooling curve, can it run through that Cascade cooling data? And if it can't, then it's not a good fit. Okay. And if it can, then that's kind of a constraint on the mass and radius, right? Or the equation. And so if you do that, you can actually constrain, for a given equation of state, you can actually constrain, again, don't take this literally, because currently doing the detail fits at this time. These are just fits by eye. You can see different masses, different combinations of the superfluid and superconductivity, trying to run it through the cooling data, which is these red points here. You can actually constrain the mass and radius very, very tightly. Okay, just for example, just going off by 0.1 in mass, you won't be able to fit it for the same equation of state gap. Okay. So Other questions? So I'm going to move on to the third topic if there's no other.
I have a question.
Sure.
So you're assuming that an equation of state, there's a correlation between pressure, energy density, and gap versus density.
No.
Okay,
So
then how do you get
that's the thing that I was saying, that I'm treating the equation of state and the gaps independently.
Okay.
Ideally, I'd like them to be consistent, but
Okay, then
there's
I'm
no
very
calculations.
confused, about how can you use cooling curves to get a better constraint on massive radius?
So I'll turn it around and say that using the data, I am constraining whether an equation of states and gap independently can fit the data. Okay, it's a game. It's a game. Okay.
This is also sensitive to the envelope assumptions about envelope.
Oh, yeah. So there's one. I wouldn't say degeneracy, but there's something else that, again, I've done the work on fitting, is that whether it's a iron envelope or a carbon envelope.
So this is for carbon.
Well, what I'm showing, these curves are all for iron, but I've got one for, I've got it for carbon too. So. And like I said, these are several months old and stuff. Yeah. Other questions?
And when you say rapid cooling here, you mean
Cooper pairing, yes. I'll just note that, so obviously some of you know there's a controversy, debate as to whether Cathay is undergoing rapid cooling. So rapid as in about 3% temperature change in over about 10 years. Okay. If it's less than that, okay, well, whether it's 0 or 3%, that still tells you something, right? That still tells you, that's still a constraint, right? So, you still can learn things about the gaps and equation of states, because again, you still need, if there's no cooling, right, the temperature is constant, right, then that tells you that the temperature is not changing over the 10 years, and so cooling curves have to be relatively constant in 10 years at the age of Cathay.
Wynn?
Yes?
I want you to react to the following. I've been talking with Dima.
Mhm.
Suppose there is no fall off in temperature. It's constant, but still the temperature is, will you need neutron superfluidity still?
No. You can fit it, if that's the difference, is that if it's 0 cooling, there's no change in temperature, then you do not need superfluid, at least for my fitting, you do not need to have, you can do it with some of the gap models, but you do not need it to have the triplet in the core.
But both Danny and Dima find that we still need superfluidity.
Okay.
So what do you say to that? I've pressed both of them very hard.
Mhm.
Suppose we know the temperature, 2.5 or 5.2, whatever, some units, and there is no cooling. Question being asked is the matter still a superfluid? We don't need proton superconductivity,
Mm.
but we still need
Let's
neutron superfluidity.
see, because
Because the crucial point in our
Yeah.
original papers was that in order to look at the slope of
Yeah.
cooling, to the proton
Yes.
conductivity, that
Yes.
is, not the neutron.
Yeah.
But you still needed the neutrons to be superfluid. I pressed both of them again.
Okay.
No.
Okay,
No fall off in the temperature. Forget proton superconductivity.
Okay, if you're
Do I still require neutron superfluidity, and both of them answered yes.
okay, if my statement is if you assume proton on superconductivity, one of the gaps, I'd have to check. I don't remember the cooling curves that I've calculated without proton superconductivity, whether they can give you zero. So,
Just one quick question.
Yeah.
Is this P wave that is making the fast cooling, or
yes. Yeah.
not the S wave?
No, no. Yeah, so the CAS-A data is, the CAS-A is sufficiently old that the crust superconductivity superfluidity does not influence it at all. It all happened, the crust effects, superfluidity effects happening at less than 100 years. So they're determining things here. Okay.
Another, if I look at the middle conclusion of the graph,
Yeah.
I mean, and the masses seem to be
Oh,
anywhere from 1.4 to 1.8. What do you make of that?
Don't take the numbers. Like I said, yeah, it was just kind of fits by eye, and yeah.
But if we were to if we believe that these exact numbers might not be
Yeah,
perfect,
yeah.
there is some set of numbers that
Yes.
we predict, then could we play the following game? Of course, we don't know the birth mass of neutron stars, but in principle, I think the following hypothesis cannot be ruled out: that all the neutron stars are born with masses roughly in the 1.25 to 1.4 solar mass range, and anything that is more massive than that, like the 2 solar mass neutron star, has accreted and so has grown by accretion, right?
Right.
So if we're in the game of making reasonable, simple assumptions,
Yeah.
let's assume that for a moment that in fact neutron stars are born with the masses of 1.25 to 1.4 solar masses, right? So then it looks like in principle you could, under that assumption and using these observations, constrain some of the equations of state.
Yes.
You could say, for instance, the one
Yes.
predicts 1.8 solar masses.
Yes, yes. Yes, you can
ruled
do
out
that.
in that.
Yes.
Although, because astronomy likes cutting down any such statement, so Vela X1, which is a high mass X-ray binary, therefore is almost certainly accreted very little since it was born, has a best mass of about 1.9 solar masses. Because the universe does this to us all the time.
No, that's nice. I didn't feel it.
Yeah.
Okay.
But as a general, I'm still confused about how you can constrain the mass and radius with cooling observations. What puzzles me is that there is such a tenuous connection between the gaps and the equation of state. If I just make the assumption that the gaps have nothing to do with the equation of state, the
Right.
physics that matters for the gap is unrelated to the equation of state. How do you get, they're completely different.
Right.
And so how, a statement like CAS-A rapid cooling requires APR to be 1.8, how do you come up with that? I'm missing something simple.
So, okay, APR, if I take APR and a particular gap, let's say take this blue curve here, because that's for a particular gap. If I just change the mass, okay, it'll change the slope and actually it'll move the curve and also the slope.
You could do that by just changing the gap.
Yeah, yes. That's why they're different curves for different gaps. Okay. But for APR and that gap, I tune the mass until I can get it to. Okay.
When Danny always keeps making the point that the envelope is very important.
Yes.
Have you considered envelopes?
Yeah. So Armin asked about that. So the cooling curves shown here are with iron envelopes, but I have analogous, not plots because I haven't made them, but cooling tracks for carbon envelopes. And it obviously changes the numbers and stuff, but yeah.
So, sorry, Wynn, to re-ask Sanjay's question, because I think it's an important one to understand what you can actually say about the masses.
Yeah.
If you fix the gap and you fix the equation of state,
Yes.
you explain how it is that you could then get a constraint on the mass.
Yes.
But it sounds like your approach is that you can independently vary P of rho and the gap. So
Yes.
if that's the case, could you not assume APR and vary the gap to get whatever mass you wanted? I think that was the question. So, and if that is not the case, it sounds as if you need some link between the gap physics and P of rho.
So if you could.
Ideally, yes. The latter is what I want. I would like.
But in your current approach, you're assuming there is a decoupling.
Yes.
So could you not pick, decide on a mass and an equation of state and just vary the gaps and make it to the data?
Yeah, I mean, and that's what Danny and we did in the original result to get the temperature of the critical temperature for superfluidity, because we just varied the gap until we can get.
No, we varied the mass as well.
Oh yeah, and the mass and stuff. But the point is, here I've taken the I've just taken the gaps that people have actually calculated rather than varying it, just arbitrarily varying it. I've just taken what people have published.
What kind of magnitude of gap are you talking about? Is this the 0.1 MeV that's the most recent value? Or some of the higher earlier values?
So for the neutron ones, this is.
Okay. See, gap energies are sufficiently small compared to the pressure, the energy density, or energy per particle.
Yeah.
At the at that particular densities, that they don't make a huge impact.
Oh, on P of rho, absolutely, I understand that. But they're also notoriously difficult to calculate. So if you change them significantly, it sounds like and maybe this is why you're emphasizing to us not to take the particular.
Yeah, exactly.
That seriously.
I mean, part of a large motivation for my part of doing this is to kind of motivate the nuclear physicists to give me or provide to the community things that we can use to actually calculate this consistently. I mean, I would love to calculate this consistently and remove this arbitrariness, but this is all that I have. Okay. So let me move on to the third topic, which Andrew briefly mentioned, and so let me go through this relatively quickly. So obviously, and that's looking at pulsar glitches and what we can learn from looking at pulsar glitches. And so obviously we know that neutron stars rotate. We detect pulsars, they're rotating neutron stars, and therefore we can track the rotation rate very accurately. But occasionally, some pulsars undergo a glitch. They undergo a spin-up, and that's shown by these plots here, where we're plotting the fractional change in spin frequency as a function of time. Okay, so what you have is that at the horizontal line is where the spin frequency is not changing, right? Or relatively speaking, it's spinning down but not changing, and then it undergoes a glitch, and it spins up, okay, and undergoes many glitches. For example, for Vela, the best studied one. And so the model that explains this actually provides one of the first evidences for superfluidity in neutron stars. And the idea of the model is that you have a inner crust superfluid that's not spinning down, because the superfluidity, in order for it to change spin rate, has to move. And if it's spinning down, it has to move out. But if the vortices are pinned so that they can't move, then that superfluid is going to be rotating at a constant rate. Right? So that's kind of illustrated here. So this inside is rotating at a constant rate, and whereas the outside, the container, the outer crust and core, is spinning down because it's losing energy as it's radiating electromagnetic radiation, right? The pulsar mechanism. Right? So the outside of this container is spinning down. Right? So at some point, there's going to be the mismatch between these two spin rates, the inside and the outside, is going to build up over time. Right? At some point, which we don't know, but the actual mechanism we don't know well, or at all, actually. The vortices unpin, so suddenly the inside I'm allowed to spin down. Okay, they unpin, they can move out. Suddenly I can spin down, and I transfer angular momentum to the outside. So since the inside was spinning faster, I kind of pull the outside with me a little bit. So I spin it up. Okay. And so that causes the glitch. okay, that explanation, you can see that it requires the inside, the superfluid, to have some reservoir of angular momentum to give me, to spin me up, spin out the outside part. Right? And you can calculate what that is by looking at the data. Right? It's just the slope of this line, that the equation's here. The amount of angular momentum that I need, I can just find from fitting the measured glitches. But what recent work by Nico has shown is that it's actually very hard to kind of drag, by entrainment, it's very hard to move these superfluid. Okay, and so you're trying to kind of spin up the outside, but it doesn't want to kind of, it's resisting a lot more than you naively expected. Okay. And so basically, you need more of the inside then. If it's resisting you, then if you have a lot more, then maybe, if you're tapping, let's say, 1% of that, if you have a lot more, then you're getting more out of it. And so that's shown here. Okay, this is, again, the fractional moment of inertia as a function of mass. Okay, so if you look at the glitches, what they require is, for different glitches, pulsars, we looked at 11 of them, and you need a moment of inertia to explain the glitches that we see of about 4 to 8%. For the best studied one, Vila, it's 7%. Okay, so you need 7%, that's up here. You need more than this. Okay, you need above this line.
What does that translate to energy in solar mass? Glitch energy?
Well, so if a typical eye, the moment inertia is 10 to 45, then it's 10 to 43.
Omega square, I need to do the omega square.
Yeah. So you have to take individual sources.
Yeah, 7%
yeah. So then you can compare, well, what do models say? How much does, models of neutron stars tell you? How much do they have? Right.
Sorry, is that at each glitch?
No.
Because 7% that you're talking about?
Yeah, well, at each glitch, but you found that value by averaging over many glitches. For Vila, it's like 27 or so, 25 glitches. So, I mean, the 7% is pretty reliable. And so these curves here are how much of, for that equation of state, how much is in the crust. So that's, on the assumption that the inner crust, it's all superfluid, because that's the maximum it can give you. Right? So I don't need to assume anything about the gap. We can do that, but you can make the assumption that it's all superfluid. Right? Because that gives you the most. Right? And that's given by these lines. And you can see that in order for example, SLY, there's just not enough moment inertia in the crust to give you 7%. Whereas for APR, this parameter is APR1, this is what I had at the time, it can only give 7% if the mass is very low. Okay, so
Mass of this particular object.
yeah, for Vila, yes. So if you look at each system, right, it's 4 to 8%, so you've got 4. So they're all. So what we're saying is that the crust is not enough. Okay, and the possible solutions, the simple one is that, well, all these 11 pulsars are low mass. Okay, because then, naively, if I say APR is the right one, and then they can all give, it can give, 4 to 8% for less than 1.4 solar masses.
Really no independent mass.
No.
Information.
So, I mean, it's a possible solution. You could, they could all be low mass, below 1.4. No, it's a possible solution. Another is that, okay, so instead of saying that they're low mass, well, what if we say that instead of just the crust, what if the superfluid extends into the core? And some gaps, like the one shown here, okay, in the crust, the gap is shown here, extends into the core. Okay. So maybe it's the superfluid is extending into the core, so it extends it enough into the core that you get the 7% that you need. So, for example, if it's, let's say the SLY is the right equation of state, right? So I need at least, an extra 2%. So maybe the superfluid extension into the core is enough to give me that extra contribution from the core is enough to give me the 2%. Okay. So that's a possible solution. Okay. That's an interesting one because then that tells you're kind of learning how much of the gap is extending into the core. But you can't tell that.
What do you mean by the superfluid gap extends into the core? I mean, why do you require the singlet gap to extend into the core? What if it just turns into a triplet gap?
Yeah, if that's the solution, then that won't help you then. Yes, but we don't know.
So why wouldn't that help you?
Well, okay, so if it's you can also tap the superfluid in the core itself, the triplet, right? But then a large fraction of the core would be superfluid. So why are you only tapping, for example, the SLY? Why are you only tapping 2%? Why shouldn't you be able to tap 20%, 30%?
Yeah, so I think that's going to be true because the singlet and the triplet neutron superfluids, if you had them coexist, the vortices associated with this U1, so there's the angular momentum vortex, that would actually thread right through both of them. You wouldn't, you can't say my vortices associated with the singlet end where the singlet gap ends. It's just going to propagate further in the triplet phase as well. So there isn't really a way of distinguishing the vortex. You can't assume that the vortex ends at that interface. Yeah. So if there's a triplet and a singlet, that vortex that you're tapping into is propagating all the way into the core.
Yeah, so but again, the question is, why are you only, if you are tapping the core, and the core has so much more to give, why is it only giving you a few percent?
Okay. No, but there are answers to that question.
Okay. Well,
it's the matter of time scale. If the glitch takes, say, below 1 minute, you can tap only the part of superfluid that can respond on the time scales of minute, and these time scales are density dependent, so you can figure out where are those regions which respond on the time scale of 1 minute or less.
Well, then
you will find that not the entire core is responding, but just a small part of it.
Well, that's the great thing. That's part of the point of the talk is that therefore you're learning about the gap, right? That's the whole point is by all means, go and calculate how much of it you're tapping and what does that say about the gap. Okay. Yeah, so let me just skip to final one is that Andrew has a paper on this recently, where you could have a very stiff equation of state, and this is a different paper, but they've plotted it in basically the same way as I showed previously. These are basically our two curves. They construct two different equation of states that can give you a lot more. Right? So the 7% for Vela, you can get that for even a 1.5 solar mass. However, if you look, and this is their mass radius plot of these equations of states. They obviously they're much bigger in radius too. So I'll leave it up to you guys to hash out whether that's a good solution or not. But, yeah.
That fights
Yeah. Yeah.
What is TF? I don't know, but L must be huge.
NL is very unrealistic equation of state.
Yeah.
That's very well.
Yeah.
So which of the equations of state in the bottom panel is supposed to work?
These two here, these two.
And that sort of fights the
Yes.
current paradigm of where the radii are.
Yes. Yes. That's. But I mean, Andrew, you
That was what we basically said in our paper.
yeah. I mean,
That it fights it.
Yeah.
you can, if I guess one way to say it is, if the glitch problem is all you're thinking about, then this is a viable solution.
So the quantification of the phrase stiff equation of state is made in terms of what? Physical quantity? What do you mean by stiff?
Well, that you're getting a very large radius.
Oh, that's a stiff?
Yeah.
Okay, that's how you're.
That's all, yeah. Sorry if I'm using it too loosely.
No, I just want to know in what sense it's being used.
Okay. Yeah. I guess I won't. I'll do this. So Simon talked about R modes, and this is. I didn't make this animation. Just somebody asked me before. But this is a example of an R mode of fluid So it's a stellar oscillation of the neutron star. Okay, it's actually a fluid motion, and it has a characteristic for the not this one, but the L equals M equals 2 has a characteristic frequency of 2/3 the spin frequency. And so in Simon's recent work, and also she talked about this one, we added this this week. They get values that's close to 2/3. Okay, and so recently we wrote a paper on if you include relativistic corrections, you can get these frequencies, and also the relativistic corrections, so they depend on mass and radius, and so if you put them on the mass radius plane for each of these spin frequencies, these are the lines you get. Okay, they're not constant. Okay, there is a little bit of curvature in there, but they're relative. I mean, okay. And since this difference is relatively small, okay, this difference is basically directly attributed to their difference in spin frequencies of these two source neutron stars. Okay, and the difference is about 150 hertz. Okay, so you can see that observationally, you can determine this line incredibly accurately. Okay. Theoretically, there's issues of, we've taken the leading order terms, so there are some further corrections to this, but I think, yeah, it's kind of tantalizing evidence, results, and if you could get a mass constraint on one of these systems, right? These lines are determined incredibly accurately observationally.
Can be or have been?
Well, they are observationally, because the spin frequencies, this line is only determined by three things: mass, radius, and spin frequency.
Oh.
Okay, and so spin frequency is determined incredibly accurately.
So when you say R mode in that.
Yeah. So, but the issue is that, the issue is that these have to be R modes for you to do this. Okay.
The massive interpretation of this.
Yeah. But as we point out in the paper, for other reasons, it doesn't seem like these are R modes. So I'll skip in the interest of time, I'll skip this. But the point is that R modes are of particular interest because they are generically unstable to gravitational radiation. So they're good sources if an R mode is active, if that fluid oscillation that you saw is operating in a neutron star, it'll generate a good amount of gravitational radiation that can be detected by LIGO, for example. But, and why it's of interest to me, and it should be of interest to the nuclear physicists, is because what governs whether that R mode is active is a lot of very interesting physics. And things not just, thermal conductivities, neutrino emission, but there's issues of the crust core transition and the elasticity of the crust. How much can the R mode oscillation penetrate into and drag along the crust? There's issues of superfluidity and whether things like mutual friction hyperons, that'll determine whether the R mode is active or not. Okay. Things like, again, strange matter, magnetic fields. So there's a lot, R modes are just rich in physics. So I think that's, at least for me, that's why they're of interest. Okay. So I'll finish up by saying the three things I want you to take away from this. The first is that I don't think I need to convince you that neutron stars are very important astronomical tools for learning about nuclear physics. Okay, and it's not just, and I've given very briefly on some of them 4 examples of. It's not just about mass and radius. Right? There's also superfluidity, superconducting gaps. There's transport properties that are important that you can learn from looking at neutron stars. The second theme that I mentioned is that I talked about is my request to the nuclear physics community to provide me with useful, astrophysically useful parameterizations of what you guys are calculating, okay? So that I can implement them in things like cooling codes and stuff. And the final kind of take-home message is that I find about neutron stars that it's interesting is that kind of linking us is that neutron stars are big objects and they're far away. But we're looking at things that are big and far away that'll help us to learn about things that are small, like nuclei, and close to us. I think that's the nice stuff.
Yeah. So as sort of a general perspective about your quest for useful parameterizations, if you talked about other things that need to be done in nuclear theory, so not just the parameterization we have currently,
yeah.
But so if you were to make a wish list of like your top 3 most important nuclear theory developments that would be useful for your studies, what would they be?
Going where my current work is, it's the gaps. It's the gaps. Yeah. I mean, well, it's in. I've used not his well, for some of them I've used his parameterizations, but I had to make up a lot of the other ones and stuff. So yeah.
Okay. Let me refine the question. Which one of the three guys?
Well, I mean, I think I will ask for the hardest one, the triplet. I mean, why settle for the easiest? Because you'll just give it to me and all.
so far where they're reliable, it is at such low density,
Yeah.
it's not of much use to put in calculation.
Yeah. So I mean, I will take anything you can give me, but if again it's a wish list, I will ask for the triplet.
It may be that we have to go backwards. I'm sorry. We're just going to have to give up on the nuclear people and determine the gas from the observations.
Yeah.
If it's cooling.
Yeah.
Fair enough. Right?
Yeah. But I mean, like I said, there's other ways that of using neutron stars to try to get at the gap. The glitch, as Sanjay was talking about, is another way.
Can you go back to your previous slide?
Yeah.
So I'm wondering if I turn on my optimistic self and imagine that we've discovered gravitational waves from our modes.
Yes.
And we have, say, found something about the R mode amplitude and maybe even a damping constant. So the frequency, let's say, stays the same, but the amplitude damps. what can be constrained in the nuclear physics parameter space with those kind of observations? What other observations we may need to learn more about?
Okay, if I just take the very simplest, does anyone need? Are there enough people that need an explanation of the R mode instability window? Raise your hand if you do. Okay, so you don't. So roughly, okay, so this is a plot of spin frequency and temperature. Okay, the brief picture is that this line delineates whether the R mode is active or not. If you're above the line, R mode is active. If you're below the line, R mode is inactive or is damped. Okay, so obviously if you're above the line, that's where gravitational radiation is happening because the R mode is active. Okay, and so if you find a source that's R mode, if you detect R modes from, that tells you from the very basic model, this is the very basic model. Okay, and so that will tell you where this, where you're somewhere above this point, so that line has to be below somewhere. And what's determining this line is at these temperatures is the shear viscosity. Okay, so you have shear. The bulk is way at higher temperatures. So yeah, so here we're only looking down here. So I mean that's already a constraint on the shear viscosity. Obviously, if you detect it in multiple sources, that would be better because again, it's kind of like the mass radius. You want to be able to trace it out. You want to be able to trace out the window.
But and that's helpful. But there's a bunch of other things you list.
Yeah, but I mean, so if you start tracing it out and it behaves in very in this plane very funny, for example, something like this. If you've got this is a different. It's a crust. It's a resonance with a crust oscillation. Okay, so if you've got sources that are here and then it kind of drops off and then here, or you've got sources in between here and here but nothing in there, that tells you what frequency that crust oscillation is at. So I mean, again, yeah.
Back to your last slide.
Yeah.
You show the cooling there. That's which system is it? The one on the right there that you show the cooling for?
Okay, so again, this is just an animation we made of the Cathay cooling.
Cathay.
Yeah. So
we seem to be in a very fortunate position where cooling is very rapid.
Yes.
And are there other systems where you can observe cooling and it's not so high? Because observation points and obviously the theory.
Yeah. Okay, so I'll put it differently because a lot of people ask questions that are kind of related to that, and also like the issue of carbon is related to it. Cathay is special because it's young, and in fact it's the youngest neutron star that we know of at 330 years old. Okay, that's what makes it useful. Okay.
It's young and it's really nearby.
Yeah, well, 3 kiloparsecs is 3.5. It's relative. I mean, there are closer neutron stars. But I mean, that's the uniqueness. So if you were able to find a neutron star of 100 years old, or if 87A, you could detect thermal emission. You probably wouldn't. It'd probably be, but so you could do this type of stuff. Then of course that would be incredibly useful, not just for us, but for lots of other people.
Watching it, it looks like you have to be in the window of about 1,000 years.
Yeah, yeah.
As long as Chandra exists, it's very important to keep
Yes.
watch on Cathay.
Oh, I should say with Cathay, we have 9 Chandra observations. We have a 10th one next year, and for those of you who know about it, the Posselt, George Pavlov's got a different observation that kind of measures that there's no change. They've with 2 data points over in 2006, 2009.
Is there those 2 data points are there in the insert, right?
No, no. I'll just. So this is their result. So this is our 7 of our 9. They don't. The 2 new ones they don't have. So this is their temperature change. They actually the Chandra cycle for next year, 2015. We put in a proposal to observe in their mode in 2015 to increase the baseline and give a 3rd point. We didn't get accepted, but they did. So at least it'll happen.
Okay.
At least it'll.
So on what time scale can you, do you need to observe to exclude other explanations for this? How predictive
No.
is this model?
So I mean, it goes back to, and I think there are other explanations for the cooling, and I mean, Armin's got one here and stuff, and I mean, it's not a unique solution, and as I think as theorists, I would say that's good. I mean, I wouldn't be a good theorist if I couldn't come up with an alternative model and stuff, and so and you know, you can always tweak things. It's just like the 2 solar mass neutron stuff.
All of these make different predictions for the cooling on.
Well, no, because I think I mean, I don't know the details of the shape of their prediction, but I'm betting that many of these can give the same shape that, you know, if I took a particular gap, particular equation state, and calculated the cooling curve, I bet some of these will be able to give me the same, in the time frame that we're looking at for Cat A, the same temperature evolution.
Some of them have problematic physics.
Yeah, sure.
Which the authors admit.
Yeah. Sure. I mean, for example, the R mode, you know, the R mode argument, well, there's no, we don't know that. I mean, as far as we think, R modes are inactive. And so.
I don't know about the Rodrigo, for example.
The gravitational wave contribution to that cooling.
Well, the problem with gravitational wave contributions, we don't know the spin frequency of Cat A. So, yeah, I think that's a.
Yeah, it is being searched for.
Yeah. Yes. I mean that's. I mean, the cooling, after full acknowledgement to the LIGO community. It was Ian Jones as part of the LIGO search. He asked me, well, you know, that they were thinking about doing the search, and he asked me, we just had the Cat A result that we detect the carbon atmosphere. He asked, well, you know, has it changed? Because has it undergone a glitch or a flare or something? And so we looked at the temperature to measure the flux and the temperature to see if it changed, and it did. So yeah, I mean, it's full credit to Ian and the LIGO team that drew us to.
What atmosphere does George use?
For his, they developed carbon atmosphere models too. Yeah.
That's a big move from him.
Yes.
Okay, if there are no further questions, let's thank Wynn again.
And for those interested, I guess Krishna is taking us on a tour at 1:30 today. So we meet by the elevators at 1:30, and we'll get a tour of the lab. Thank you again.
Okay, so the 3 o'clock talk is by Jim Latimer.